Hello everyone, in this video we will cover the section 14.4. In this section we will see tangent planes, linear approximations and differentials for functions of two variables. First we will see the definition of tangent plane for a function of two variables graphically and theoretically. So we suppose a surface bigger S has equation Z is equal to f of xy, where f has continuous first partial derivatives fx and fy with respect to x and y, and we take any point on the surface P whose components are x0, y0 and z0 on this surface. As in the preceding section, we let bigger C1 and C2 be the curves obtained by intersecting the vertical planes y is equal to y0 and x is equal to x0. You know, when we intersect this surface bigger S with the vertical planes which are given as x is equal to x0, y is equal to y0, you know, the normal vector of the first one, x is equal to x0, has the components 1, 0, 0, this one. This is the normal vector, and we know normal vector is perpendicular to the plane, which means this plane is vertical to the YZ plane. Okay, YZ plane. Therefore, when we intersect this surface, if also you can see in the section 14.3, if we intersect this surface with the plane is x is equal to x0, which is obtained by using the first component of the point P, we obtain the curve C2. We cut this surface with a vertical plane parallel to the YZ plane, and we obtain the curve C2. Okay, and similarly, the normal vector of the second one has the components 0, 1, 0, y is equal to y0, this one, and this is perpendicular to the xz plane, which means the second plane, which is obtained by using the second component of the given point on the surface, is parallel to the xz plane. Therefore, when we cut this surface with this plane, we obtain the curve C1 graphically. So we have two special curves on this surface which are bigger C1 and bigger C2. And the point P is lying on both curves C1 and C2. This is the common point of these curves on the surface. Also, this is a point on the surface. Therefore, at this point we can sketch tangent lines to these curves which are given as bigger T1 and bigger T2. You see the red lines which are the tangent lines to these curves at the point P. And using the direction vectors of these lines, tangent lines, we obtain a plane passing through the point P. Actually, this is tangent to the surface at the point P by using the direction vectors of the tangent lines, bigger T1 and bigger T2. So we have two special curves like this. The common point is the point P on the curves. They are lying on the surface whose equation is given z is equal to f of xy, and then also we sketch the tangent lines to these curves at the common point like this. Of course, we have the direction vectors of them, and by taking the vector product of them, actually we obtain another vector which is perpendicular to these vectors, let's say little n, and by using the point P and the vector n, so we obtain a plane, okay, such that the vector n is the normal vector of this plane, and the tangent lines are lying on this plane. So this plane is called the tangent plane to the surface at the point P, and it is called the tangent plane of the function f at the point P, and it contains both tangent lines bigger T1 and T2. This is the geometric interpretation of the tangent plane, and also we can find the equation of this plane by using the direction vectors of the tangent lines. If you remember from the preceding section, the direction vectors of the tangent lines T1 and T2 are actually the partial derivatives of the function f at the point bigger P, because first let's remember the general formula for scalar equation of a plane in three-dimensional coordinate system. If you know the components of the normal vector, let's say a, b, and c, and we know a point already on this plane, which is the point bigger P, so we can write its scalar equation, which is in this form. You see, a times x minus x0, b times y minus y0, plus c times z minus z0. So to get a simple expression for this equation, so we divide every term here by the number bigger c, which is the third component of the normal vector. Normal vector is obtained by taking the vector product of the direction vectors, and the direction vectors will be the partial direction vectors. So by dividing this equation by bigger c and writing little a as this number and b is equal to this one, to get more simple expression for the equation of the tangent plane. So after dividing bigger c, we obtain a over c, b over c, and writing them to the right hand side, we obtain minus a over c times x minus x0 minus bigger b over c times y minus y0, and c over c is equal to 1. Therefore on the left hand side we have z minus z0. On the right hand side, to get a simple expression, instead of the constant we write little a and little b, you see. So this is the equation of the tangent plane to the surface at the point bigger P. So to find the values of the constant coefficients a and b, so we will benefit from the geometric interpretation. So the intersection of the tangent plane with the plane y is equal to y0, which is parallel to the xz plane. Okay, it is parallel to the xz plane. So we obtain the tangent line T1. Okay, tangent line T1. If we cut this plane with the vertical plane in this form, so we obtain the tangent line T1. Tangent line T1. So we have a line for the intersection of the tangent plane and the plane y is equal to y0. So theoretically this common line can be obtained by writing y0 for y, namely by solving these equations together. So we write z minus z0 is equal to, writing y0 for y, we get 0 for the second term here. So we have a times x minus x0. So you see this is the equation of the line in the xz plane actually, if you consider two-dimensional case. So a becomes the slope of this equation of the tangent line bigger T1. Therefore the slope, you know, is equal to the derivative of the function, and the derivative of the function is actually the partial derivative of f with respect to x, since we consider the variable y as a constant here. Therefore the slope becomes the derivative of f with respect to x at the given point. Similarly, to get the intersection of this tangent plane with the plane x is equal to x0, which means now x is a constant. So the common solution of these planes gives the equation z minus z0 is equal to x0 minus x0 becomes 0. The first term is 0, so we have b times y minus y0, which must represents the tangent line t2. So since we consider x as a constant, so the slope of this tangent line becomes the derivative of f with respect to y at the given point. So writing this to the equation of the tangent plane here, so we obtain a formula for the equation of the tangent plane to the surface at the point, which is written here. So it is enough to find the values of the partial derivatives of the given function, which represents a surface in three-dimensional coordinate system, and write into the formula. For example, let's find the tangent plane to the elliptic paraboloid given here at the point 1, 1, 3. F of xy is a polynomial. Easily we can find the partial derivatives by considering one of the variables as a constant. If we consider the variable y as a constant, so the derivative of f with respect to x is equal to 4 times x, which is the derivative of the first term, and the second one is corresponding to 0 since it is a constant. Similarly, we can find the second one, and the values of them at the given point 1, 1, 3. So x, y are equal to 1 to 1, z is equal to 3, which is obtained from here, writing 1 for x and y. So we have the values of the partial derivatives, which are the slopes of the tangent lines t1 and t2. So this equation gives z minus 3 is equal to 4 times x minus 1, 2 times y minus 1, which is equivalent to the equation z is equal to this one, writing to get doing necessary computation. And you can see easily its normal vector is 4 to minus 1, writing the variable z into the right hand side. Okay. So now we see the definition of linear approximation for functions of two variables. In general, we know from the equation 2, this is the equation of the tangent plane at the point P to the surface given as z is equal to f of xy, that an equation of the tangent plane to the graph of function of two variables at the point. So we consider general case for any point on the surface S when we know the values of the independent variables x and y, which are denoted by little a and b. The third component is the image of this point under f, which will be the third component, f of a to b. So using this concept, using this expression, so the equation of the tangent plane becomes z minus z0 is f of a to b is equal to the partial derivative of f with respect to x at the point a to b times x minus a. Instead of x0, y0, we write a and b, and fy a to b times y minus b. And you can see here, and writing minus f of a to b to the right hand side, so we have z is equal to f of a to b and this part. So the linear function whose graph is this tangent plane, this is actually another form of the equation of the tangent plane, gives a special function which is called the linearization of f at the point a to b, and it is denoted by bigger L of xy, whose value is given in this form. And using this equation, using this definition, we can find an approximation for the value of f writing f of xy is approximately equal to the linearization of the function f, namely f of xy is approximately equal to bigger L of xy. It gives an approximate value for f near the given point a to b. Sometimes we cannot find the value of f easily by using its definition for some hard points. Also, we cannot use a calculator for finding the value of f. So in these cases, we benefit from the approximation written here to get easily an approximate value for the function f. So if the partial derivatives fx and fy exist, namely we can define the partial derivatives for a function of two variables near the point a to b and they are continuous at this point, then we say f is differentiable at that point. This is the definition of differentiability for a function of two variables, and it is given by a theorem. So let's understand what means linearization of a function of two variables by solving an example. A function is given here, x times e to the power xy, and we will show that it is differentiable at the point 1, 0, and we will find its linearization, and also we use the linearization of this function to get an approximate value for f at the point 1 to 1 and minus 0 to 1. And you see 1 to 1 is close to the number 1, minus 0 to 1 is close to the number 0. Therefore, this point is near the point 1, 0. So the partial derivatives to find the linearization of f according to the formula written here, first we need to find the partial derivatives, you see. Therefore, first we find the derivative of f with respect to x and with respect to y. If we consider the variable y as a constant to find the derivative of f with respect to x, so actually we have x times e to the power 2 times x, and we consider the variable y as a constant like the number 2, or we can write 3 and so on, any number. Y is any number in this case to find the derivative of f with respect to x. Therefore, we have a multiplication of two functions, x and exponential 2x. According to the product rule, we write the derivative of x is equal to 1 times the second function e to the power xy plus the first function x times the derivative of the second function. What is the derivative of e to the power 2x? It is equal to 2 times e to the power 2x. In place of 2 we write y. Therefore we have y times e to the power xy, which is written here. Similarly, you can find the partial derivative of f with respect to y by considering the variable x as a constant, and the values of them at the given point will be 1. You can see, writing 1, 0 for x and y, we can obtain 1. So you see fx and fy are continuous functions because exponential function is continuous everywhere. Therefore, from the theorem, we say f is differentiable. So the linearization, what means differentiable for a function? So we can take the derivative of f at a given point. So the linearization according to the formula becomes f of a to b, f of 1 to 0 plus the partial derivative of f with respect to x times x minus a, x minus 1, and fy times y minus 0. After necessary computation, so we obtain x plus y. So the corresponding linear approximation will be, this is the linearization of f, according to the formula, f is approximately equal to its linearization. Therefore, we write x times exponential xy is approximately equal to x plus y. Okay, f of xy is approximately equal to bigger L xy. In the example, the function is equal to x times exponential xy, and linearization is equal to x plus y. So we have a very simple expression in place of x times exponential xy. So easily we can find an approximate value for f at the given point 1 to 1 minus 0 to 1. Just we add them, so we obtain 1. And when we compare this with the actual value of f at this point, namely we write directly the numbers for the independent variables in the definition of f. So actually we have 0.98 so on. So you see they are very close to each other. So for some very hard digit numbers, we will get very close values for them. Therefore, it is useful for finding the values of f approximately in applied science. So now we will see the definition of differential for functions of two variables. First, let's remember the differentiable function for one-dimensional calculus. For a differentiable function of one variable, y is equal to f of x, so we define the differential dx to be an independent variable, since x is the only independent variable of this function. Y is the dependent variable. That is, dx can be given the value of any real number. Okay, dx can be any real number because it represents an independent variable. So differential of y is defined as, so from here actually we use the chain rule. Dy, the differential of y, is equal to the derivative of f times the derivative of inner function x, which is represented by dx. Or in Leibniz notation we can write del f over del x times dx. So for a differentiable function of two variables, z is equal to f of xy. Here we have one independent variable, but here we have two independent variables, x and y. So we define the differentials dx and dy to be independent variables. That is, they can be any number, like the one-dimensional calculus. Then the differential dz, which is the dependent variable, also called the total differential, is defined by dz. So from here we take the derivative of this equality. Actually we differentiate this equality. So dz is equal to, so first, since we have two independent variables, of course we will use the partial derivatives of the function f. So by considering the second variable first as a constant, so we take the derivative of outer function, which is the partial derivative of f with respect to x, times the derivative of inner function x dx, plus the partial derivative of f with respect to y by considering the first independent variable as a constant, times the derivative of inner dy. In Leibniz notation, it can be written as del z over del x dx plus del z over del y dy. The first term is corresponding to the independent variable x, the second term is corresponding to the independent variable y. And you see, actually we have two different independent variables. This is the generalization of the differentiability to two-dimensional calculus. You see the difference between them. And another notation for the total differential is written as del df. Okay, df. Sometimes we use df to show the total differential for functions of two variables. So if we take dx as the change in the independent variable x, written as x minus a discriminant dx, and dy as discriminant y, which is the change in the variable y, written as y minus b, then the differential of z, dz or df, differential of f, is equal to fx x minus a. Instead of dx we write x minus a, instead of dy we write y minus b. So in the notation of differentials, the linear approximation can be written as fxy is approximately equal to f of a to b, and the remaining part will be the differential of the function. If you look at the formula of the approximation, except the first term, the remaining ones are equal to the differential of the function. Therefore, the approximation becomes, in the notation of differentials, f of a to b plus dz. Okay, this is the notation for approximation using differential. For example, let's consider the function x squared plus 3 times x times y minus y squared, which is a polynomial. Let's find the differential dz. According to the formula, we will find the partial derivatives. You can find easily 2x plus 3y by considering the variable y as a constant. The derivative of x squared, 2x, the derivative of middle one is 3y, and the last one is 0, and so on. You can find easily. And if x changes from 2 to 2.0 and y changes from 3 to 2.96, which means x is equal to 2, namely dx is equal to 0.05, which means we write actually 2.05 minus 2 for discriminant x, and dy is equal to similarly 2.96 minus 3 becomes minus 0.04. So we obtain the differential after writing the necessary numbers into the variables written here. So the differential, the total differential, becomes 0.65. So the increment of z, which is given here, namely we find the value of f at the point, which are the second numbers, minus the beginning numbers 2, 3, using directly the definition of the function f, we obtain the increment of z as 0.6449. Now, so we notice that the increment of z is approximately equal to the total differential of the z. Okay, but dz is easier to compute. Therefore, sometimes in applied science we take the approximate value of the differential. For example, the base radius and height of a right circular cone are measured as 10 centimeters and 25 centimeters respectively, with a possible error in a measurement of as much as 0.1 centimeter in each. So use differentials to estimate the maximum error in the calculated volume of the cone. So when we measure the radius and height of this cone, so we have a possible error. So it takes 0.1 maximum value. So our aim is to estimate the maximum error when we measure the volume of this cone. So the cone is given here graphically. The height is represented by h, and this is the radius of the cone, and we know the values of them. With a possible error in the measurement of them, maximum it is equal to 0.1, and you know the volume of the cone is equal to pi times r squared times h over 3, and the volume is given here. So actually the volume of the cone is a function of two variables. It is depending on the radius and the height of the cone, circular cone. Therefore, we can consider it as a function of two variables. So the value of the volume is approximately equal to actually the value of the volume times the error. Okay, the value of the volume times the error. If we look at the approximation here, f of xy is equal to f of a to b, namely v of 10 25 plus the differential of the volume. So the differential of the volume represents the possible error of the volume when we measure it. So to find the differential of the volume, we will benefit from the formula of the differential. First, we take the derivative, the partial derivative of the volume with respect to r by considering the variable h as a constant. So it is equal to pi over 3 times h times the derivative of r squared to r. Similarly, by considering the variable r as a constant, we obtain pi over 3, which is a constant. R squared is a constant here. Just we take the derivative of h, which is equal to 1 times the h. Okay, this is the differential of the volume. So you can see here. So to estimate the largest maximum error in the volume, we take the largest error in the measurement of r and of h. The maximum value is given in the example 0.1. Therefore, instead of dr and dh, we write the maximum value error. To find the maximum error for the volume, 0.1, and we know the values of the radius and h. They are equal to 10 and 25. Writing them also into the formula written here, so we obtain the maximum error for the volume. Okay, the maximum error in the calculated volume is about 20 times pi. Thank you.